All right, we are live. Let me double check that this is actually working on YouTube. And that it's showing up on Mardev. Yeah, it looks like it is. You're working on it? Yep. Okay. So welcome everybody, thanks for joining. Last week we read the first 5 sections of the white paper, and I think that went pretty well, if slowly. I spent about 3.5 hours. And so this week we're gonna pick up where we left off, or back up just a little bit from where we left off, and restart section 6, which is all about whom. Let's see here. So we'll be looking for questions in the urbit chat, which is mardev/whitepaper. You can join that from talk on your urbit and post any questions you have, and we'll be stopping regularly to check that and answer any questions that come up. So with that totally off the cuff and awkward intro, I'm going to pass it over to Master Harlot, who will be reading section 6.
All right, here we go. Start it over again. All right, so section 6, Hoon, a strict functional language. Hoon is a strict typed, higher order, pure functional language which compiles itself to Knock. While Hoon is not much less expressive than Haskell, it avoids category theory and aspires to a relatively mechanical, concrete style. A very rough comparison, Hoon is to Haskell as C is to Pascal. Like C, Hoon is a relatively thin layer over the compiler target Knock. 6.1 Semantics. The semantic core of Hoon is the backend compiler function mint, which is 1,500 lines of code for type inference and code generation. Mint works with 3 kinds of noun: knock, a knock formula, twig, a Hoon AST, and span, a Hoon type, which defines a set of valid nouns and their semantics. The type signature of Mint is buck, hep, pal, cal, is it? Is that kel?
Yeah, kel.
Kel, span, twig, care, kel, span, knock, care, par, sem. That is, Mint takes the subject type and the expression source and produces the product type and the knock formula. Understanding the span system gets us most of the way to understanding Hoon. We'll do this in 2 steps. First, we'll explain a simplified version of span, listing 2, that doesn't support adequate polymorphism. Next, we'll extend it to the real thing. Okay, so why don't we pause real quick?
Yeah, I think that's a good idea. Anybody on the call have anything jump out from that as a question? I think I want to try to rephrase it in my own words, but
yeah, it's a good idea. Okay. Right.
It's worth re-emphasizing that these are indeed 3 different kinds of nouns. Knock is obviously a knock formula, which is just a tree of numbers, of atoms, unsigned integers. Twig, which is a Hoon AST, abstract syntax tree, which is to say it is the structured output of the parser. It's a tree of nouns that represents all of the possible syntactic combinations of Hoon source. And then span, which we've talked about before, and you'll see it talked about quite a bit, but it's really important to remember that a span is simply a noun which describes the type of another noun source. And then span. All right, so I don't know if those help a little bit. It wasn't entirely clear to me reading through initially that, for instance, this source code in listing 2 is actually a mold, which is to say it's a constructor function for the actual noun, which is a span. So this source is a validator function showing you the shape of various possible span.
Are you talking about 6.1.1?
Listing 2, yeah, 6.1.1. That's right.
Yeah, listing 2. Okay. Now, up above it says the type signature of Mint is buckhep, et cetera, et cetera.
Right. So what that's describing is that's describing a function, right? That is actually Hoon syntax for the signature of a gate or anonymous function.
Right.
So at the beginning you have span twig, right? If you look at the buckhep, it has 2 sub expressions in it. The first one is the validator for the argument, for the sample. And so this is describing a function which takes 2 nouns, the first of which is a span and the second of which is a twig. Right? So it's a function that takes a span and a twig. And then the second expression here is describing the type of the product of the function. So the function takes a span and a twig and produces a span and a knock formula.
Okay.
So that should help the rest of the, which is to say, it takes the subject type and the expression source. So you have a Hoon expression. You pass it through the parser, you get a twig out of that, which is a structural representation of the expression. In order to compile that, you need to know the type of your subject. Every Hoon expression is evaluated against a noun, against the subject of that expression. And so the simplest type is obviously just noun. We don't know anything about the subject. This expression doesn't reference the subject, but it could be much more complicated than that. And then the compiler produces a new span, which is the inferred type of the product of the expression, and the knock formula, which represents the actual compiled expression.
Which in themselves are combined into a cell, right? The both, and is that the return type is a cell?
So you could say that the function takes a cell of the subject span and the Hoon twig and produces a cell of the product span and the knock formula that would produce that product. Okay,
very nice. Would you mind reading that expression there, the type signature of Mint, the buckhep? So you would say it's a gate, right? The definition of a gate in which the sample is the span twig cell.
That's right.
And the product, but it's not an actual product. It's just the mold. Is it the mold of the product, or?
That's right. Right. So what buckhep is for validating functions. Imagine that you're writing, a high order function, like a filter function with a callback, if you will.
Okay.
Hoon is strictly typed, so you might want to you want to be able to represent the type of the function that you're accepting.
Yeah.
That's what buckhep is for. So this is basically asserting the type signature of a function, to use normal programming terminology.
Right. And what family again? Because I know that the library is divided into families according to their
twigs themselves. The runes are divided into families, and buck is the family of molds. And so we'll get into molds in more detail, but molds are type constructors.
Okay.
In their simplest representation. And the other thing to really note, and I wish I had prepared a couple of slides for some of these listings just to put them on the screen really big, but listing 2 on page 16, section 6.1.1, everything inside that listing is a mold. Those are molds wrapped in molds wrapped in molds. Span is itself, a span has a complex span, let's say.
Okay, cool. So Russian dolls.
Yeah, absolutely.
All right. Yeah, that's a good explanation. Thanks.
Sure, yeah. So anybody else on the call? And I'll check the
Check that
here.
chat.
Nothing yet.
Yes, nothing.
Okay, I'm good.
Okay. Cool. Anybody? Yeah. Okay. Cool.
I don't know if this is maybe this is for the best for the next section. I was going to ask why there are when listing 2 says that there are shows faces P and Q on each of the parts of the expression. Is it saying that there can be faces there, or that there must be faces there?
That is a very tricky question to answer. I don't really think it's saying either.
Okay.
So a face is, you can think of a face as metadata in the type.
Yes.
Right? And so a noun could nest within that span represented by, say, the cell mold in that listing without having those faces. But if you cast it to span, or if you did a pattern match with the fits or what tis twig, then the faces would be there. But they don't have to be there in order for the noun to be cast or molded to that type.
And if they aren't there, it assigns itself an internal name.
Sorry?
And if there are no faces, then it's given an internal name, or is it just?
It's hard to answer abstractly, honestly, because it depends on what you're doing.
Okay, maybe if we read it.
Yeah, I think we'll just go forward. And there's a discussion of limb and wing resolution on the next page. So that'll at least bring us back to some of this.
Wow, it's we read this last time, but it's still like virgin eyes over here for me.
Here's what I would say, because last time we were kind of having fun with the actual runic pronunciation, but it's hard work.
Yeah.
Why don't you just read the buck noun, for example? Just say noun.
Okay.
Just read the words of the expression. I think everybody has a copy of the white paper.
Or why don't you read that? Why don't you read that?
Okay, sure. So 611 is a simplified span. And again, this is a version of span that does not support polymorphism. You know what? I'm actually going to back out of what I said because otherwise it's too redundant. All right, here we go. Buck noun is the set of all nouns. Buck void is the set of no nouns.
Right.
And actually, you know, I'm going to take 1 second here. I'm going to plug at this point the Hoon docs that I wrote. I'm putting a link to them in the urbit chat because I have an extensive discussion of span and mold in there. And I think that's, I tried to clarify it as best I could there. But I just want to remind everyone that at a very fundamental level, type in the sense of a programming language describes the set of, describes a set of possible values. So when we're talking about types abstractly and different types, a type is sort of a label for a set of values that fit within some kind of category. So noun, you can think of buck noun is the set of all nouns. It's a label for the set of all nouns. And buck void is the set of no nouns.
Sure.
I have to look for the pronunciation because I don't know it. I'm going to skip the syntactic pronunciation.
For which one?
Cell span span is the set of all cells with a head P and tail Q. So cell, it just wraps two other spans, you know, for its head and tail. And then fork, set span, is the union of all spans in the set P, which is to say that a noun that has a fork span could be any one of the set of spans in that fork. A whole span with span P and twig Q is just a lazy reference to the span of ment PQ. Since Hoon is a strict language, infinite data structures are always expanded manually. A buckface P term Q span wraps the label P around the span Q. Remember that Hoon has no concept of scope or environment, therefore it is nothing like a symbol table. For a discussion of name resolution, see below. A buck atom is an atom with two twists. Q is a unit, Hoon's equivalent of maybe in Haskell or nullable in Rust. If Q is sig, null, 0, any atom is in the span. If Q is the cell of sig and x, where x is any atom, the span is a constant. Its only legal value is x. P in the atom is a terminal used as an aura, or soft atom type. Auras are a lightweight advisory representation of the units, semantics, and or syntax of an atom. Two auras are compatible if one is a prefix of the other. For instance, ACT means UTF-8 text, least significant bit low. ACT-A means ASCII text, and ACT-TAS, or TAS, means an ASCII symbol. ACT-U means an unsigned integer, ACT-UD an unsigned decimal, ACT-UX an unsigned hexadecimal. You can use a ACT-UD atom as an ACT-U or vice versa, but not as a TAS. I don't think that's clear. We'll come back. But auras are truly soft. You can turn any aura into any other statically by casting through the empty aura ACT. Again, auras are advisory. These definitions are just conventions. Hoon is not dependently typed and can't enforce data constraints. A buck core is a code data cell. The data or payload is the tail. The code or battery is the head. P, a span, is the span of the payload. Q, a name twig table, is the source code for the battery. Each twig in the battery source is compiled to a formula, with the core itself as the subject. The battery is a tree of these formulas, or arms. An arm is a computed attribute against its core. All code data structures in normal languages, functions, objects, modules, etc., become cores in Hoon. A Hoon battery looks a bit like a method table, but not every arm is a method in the object-oriented sense. An arm is a computed attribute. A method is an arm whose product is a function. A Hoon function or gate is a core with one arm whose name is the empty symbol buck, and a payload whose shape is a cell of sample and context. The context is the subject in which the gate was defined. The sample is the argument. To call the gate on an argument x, replace the sample, a tree address 6 in the core, with x, then compute the arm. Of course, we are not mutating the noun, but creating a mutant copy. All right, that's 611. And I think there's several things.
Could you go through the listing 2 line by line and just describe in your own words just explain each one in your own words?
So the first thing to note at the very beginning is we have less. We have 2 plus signs followed by 2 spaces.
Yep.
You know what? I'm going to share my screen real quick so I can highlight which parts of this I'm talking about. Where is the screen share? Yes. All right. You can see that?
Yep.
Okay. So the 2 pluses and the 2 spaces afterward, and then a name, a symbolic name.
Just zoom into that.
Yeah, sure. How's that?
Yeah, that's good. Thanks.
That means that we're in an arm of a core already. And I'm not going to go into too much detail about that, but that's what that means. That syntax means that this is an arm of a core. So moving along here, the indentation makes this a little bit hard to read. But this here, everything that I've highlighted is a single expression. And it has 2 sub-expressions. This one and this one. So, buckpat is, I'm going to use slightly imprecise terminology just because it's so much easier. These are all molds. Molds are all constructors for a particular type, which is to say that they produce nouns with a consistent span. But I'm just going to talk about the spans that they produce and not that layer of indirection here. So buckpat is the mold for a fork between an atom and a cell. So you can have a type, a union type that represents the choice between an atom or a cell. And if it's an atom, it's the first sub-expression, and if it's a cell, it's the second sub-expression. So if the spin is an atom, it is the buckwhat here, which is just a simple fork between a set of choices. It's either noun or void, which is to say, again, we're looking at the mold. So the noun in question would be send noun, as in %, or send void. So these are just, the absolute opposite ends of the spectrum. Send noun would mean the set of all nouns. We don't know, in other words, we have a noun and we don't know anything about it, right? It could be any possible noun. And then send void would mean this is a void type. No noun matches this type. Void is the inferred type of an expression that crashes, for instance. If the span is a cell, we move on to this next expression here. Now, buck-sen is a tagged union, or a discriminated union, or I don't know what the other names for them.
Hold on, before you go. So this is an arm, right, of a core.
Yes.
So when you're talking about if it is a noun or if it's not, you're talking about the battery. Is that right?
No.
Battery of the core.
So it's more confusing because we're actually dealing with a lot of cores here. Like, I couldn't even count how many cores we're dealing with in this one expression. So that is not really relevant to the discussion of span. I just wanted to mention it while we're here. You can think of everything else here, right? So the arm, again, is a computed attribute. And so to evaluate the arm, which is, again, one of the formulas within the battery of a core, if you evaluate the arm, you get this expression that I've highlighted, which is a function. It's a constructor function for a span.
Okay.
The whole thing is. So it in question is a noun. Remember that span means a noun that literally, concretely describes the type of another noun. And so that noun, for each of the choices here, we're describing some possible noun. That noun would be the sample to the gate that's produced by the expression that I've highlighted here. But at that point, there's so many layers of indirection. So again, this is all just validator / type constructor for the literal noun, which describes the type of some other noun.
Okay. Yeah, that makes sense.
And so Buck-Sen here is the tag union, discriminated union, some type. There's other names too. And basically the reason for it is that it can be hard to choose when you have a fork, when you have a single type that could be one of many possibilities. It can be hard to distinguish between them. So, you know, Buck-Pat is one way to distinguish between them. You have an atom or a cell. That's really easy. Well, then this is just a generic fork, Buck-What. Now, in the case of these, you know, constant symbols like noun and void here, it's very easy to tell the difference between them. But if you have complex types in there, it might not work real consistently, or it might not be obvious how it would work. So to have the most robust representation of a wide variety of types, you use a tag union, which is to say that you literally tag each branch of the fork, every possible subtype, if you will, with a label. And so the labels here are atom, cell, core, face, fork, and hold. And so, you know, you pay the cost of having an explicit label in the noun itself, but the advantage you get is that, you know, it's just obvious which branch it belongs to, and you can, you know, distinguish between types of arbitrary overlap or arbitrary complexity. So each entry here is a separate branch, is a separate potential type. You know, so the way that they're formatted here makes it very nice, because each of these rows from this position on the screen to the right represents a branch of the type, because you have 3 layers, you have 3 separate forks here, and they effectively represent the branches noun, void, atom, cell, or so on. Okay, so to go through the individual branches real quick.
Yeah.
An atom is an atom, right? So in the initial analysis, it's worth remembering an atom is an unsigned integer of unbounded size, of any size. So that's the base case here. There's 2 additional levels or pieces of information about a specific atom that we can have. The first is this term, and term is just an alias for a symbol, which is to say send something, send noun, right? Send noun would be a symbol, send void would be a symbol. So the term is just a symbolic descriptor of the type of the atom that we have. But again, it's sort of a nested type system within the span system. The span system can test and validate the shape of a cell. But because Hoon doesn't have dependent types, it can't test and validate the contents of an atom. All it can do is describe the intent with which that atom was created or expected to be used. So this term here is the aura, and the aura is something like U for unsigned, or T for text, or P for the phonetic base, which is to say all the ship names that you use. There's many different auras. There's auras for dates, for durations, for unsigned, signed, and floating point numeric types, and there's just simply labels. The second part here, the unit atom, is the distinction between a normal atom and a constant. So a normal atom, from a type standpoint, is really just the label, right? Any unsigned integer, you know, could nest within that type. You know, you could cast any atom whatsoever to the type of a particular atom here, unless it's a constant. If it's a constant here, then this unit isn't null. It's a null prefix cell of some specific atom. And then the type is saying only this literal specific atom is valid for this type. And by the way, that's what the buck something represents. Buck noun and buck void here are what we call leaf molds, and they're molds that match a constant atom. So buck noun matches the constant symbol noun and nothing else. And sen noun is the constant symbol noun. So if you inspect the span of, let's see, I'm not going to live code right now. I'll throw it in the chat. You can inspect the span with a single question mark or a double question mark in the dojo. No, it's been taking too long to do that. So I'm going to move on. Maybe we can come back to this. Cell, this one should be pretty simple, right? All this is wrapping two other spans, one for the head of the cell and one for the tail of the cell. Core is a little bit trickier here, even in the simplified span. The head here, P.
Hold on, Joe. Are you sure you don't want to do that?
Well,
that'd be good.
Wait. Well, I think the core is the one that, like, methodically it gets more confusing. Face, everything until we get to core and the text makes pretty good sense to me. It's even the face. Like, the face stuff makes sense if you've read the paper and you've gotten to the tree addressing stuff. But yes, are you saying that maybe we want to do core last because it's such a mind-melting thing, or?
Oh no, I was saying if you wanted to type out that dojo or the urbit channel stuff.
Yeah, I'll try to read through this first, and then let me read through the rest of the listing, and then we can go back and forth. Okay.
Okay.
Because I'm having too much trouble jumping back and forth. I'm losing my train of thought.
Yeah.
So core, P in core, the first face here is the span of the payload. Right? A core is just two things, right? It's a tree of knock formulas, and then it's something else. And that something else could be a wide variety of things depending on how the core is being used. But it's just generically something else. And that something else is what's described by P here. We typically say it's a code data cell, but that data could have more code inside of it, and it could get very complicated quickly. So P is the span of that payload, the second part, the tail of the core cell. Q here is a map from a term, which again is a symbol, to another span. Now, this is for the battery, which is a tree of arms. So this maps from the name of the arm to the span of the product of the arm. And now I believe it said it already, but we may, it might not have, it might have been somewhere else. The span of each of those arms is going to be a hold. It's going to be deferred, but we'll get to that. So face is very simple. Face is just something that gets wrapped around a span that already exists and puts a label on it, right? So term is once again a symbol. A symbol is an leading alpha, lowercase, alphanumeric worm case, which is to say it's the symbol constraint for the language. It describes the valid syntax for names, right? So you could have span, you could have span 1, you could have span -2, but you couldn't have, the number 1 and then span. You couldn't have title case span, You couldn't have span underscore, back or something. So anywhere you see term means symbol. Symbol means a valid whom symbol, a valid name in whom. And all face does is wrap a name around a span. Fork, we've talked about before. It means that you could be any one of a set of spans. And then hold is manual laziness, which is to say, it's the product of compiling the twig Q against the span P. So you can have an infinite span in a strict static language simply by deferring the inference. Okay, so that ran through that. Let's talk about that a little bit. I don't know how clear I was, honestly. I don't have a sense. So you guys, you tell me.
A couple of things clicked for me with that description. One thing is, looking at this and having looked at knock, I keep looking at thinking, it's turtles all the way down. It's just unsigned integers. Nouns are just, an unsigned integer or a cell of other nouns, right? But looking at face, and you say that the term is sort of a built-in type, if you will, for a actual human readable label, right? So that's kind of that's the buck stops there to a certain extent, like knowing that term, that the compiler or Mint or wherever this type system really lives does right there have a sort of built-in type that specifies a human readable label. Like that's a beachhead onto which I can establish kind of some understanding, I think, of how we get from integers to something that a human can comprehend, right, and reason about and program with. So
I'm going to jump in right here, Chaz, and say that in a sense you're absolutely right, but in a sense I have to take your beachhead and demolish it. Those symbols are atoms. Those symbols are unsigned integers.
Mm-hmm. So the only type in all of this isn't even really enforced, but it's only there's the whole Aura system that sort of suggests types.
Advisory.
Right? Advisory.
Right.
Types.
Well, and so to talk about enforcement, you have to specify a context, right? In the sense of a typecast, they're not enforced. But when you talk about the symbol constraint and about names in the language, those constraints are enforced by the parser, for instance, right? So but it's worth looking at the expressions that Brian put in the video chat here. Hey, Brian, would you duplicate your messages in the white paper room? Because that shows exactly what I'm talking about.
Yes, here. Let me put that in right now.
I just want to save those for posterity. But what he's showing here is the span of the symbol elephant.
Where are you looking?
This is in the video chat of the Hangout.
I see.
Brian's going to put that in the.
Let's see. The correct room is mardev.urbit.org/whitepaper.
That's right. Yeah. Well, and so you can.
I'm there.
You have an Urbit running?
Yeah.
Yeah. So just join mardev/whitepaper and talk.
Sure. I'm subscribed to that channel. I just need to set it as my audience. Here we go.
So looking at the span of the symbol elephant, you can see that it is a cell with many parts nested within it. So the head of the cell is atom, which matches what we would expect. I won't talk about them as cells because it gets too confusing with the right association. So the tuple, the first item of the tuple is atom. The second item of the tuple is the symbol TAS, which is the aura TAS, which is the symbol constraint. Then the third item of the tuple is another cell, right? The head of that cell is null. The tail of it is this really long unsigned integer. 8.389.750.257.028.000.869. That is the symbol elephant.
Sorry, question. Just can someone remind me how to cut and paste code into talk?
Unfortunately, you can't paste that as code if it was a Dojo expression.
What if you do it with the pound symbol?
Yeah, the pound symbol is how you do code, but it's not whom. Here, let me do this real quick here.
Let me see if I can do that.
Oh, I can do some span examples.
Oh, here.
All right, I'm just going to take a second and write some examples. We'll ignore how they work for now.
Mm-hmm. Okay.
Wow, my system is just crawling from the screen.
Brian had a nice visual of his dojo up earlier.
I did. Here, I can do it again, actually.
Yeah, do that. And then just shout stuff out you want to have typed in, Joe.
Yeah, that'll work great.
Yeah, so just the exact same code that you put in the Hangout chat.
There we go. So.
Okay, cool.
What? 2. Gives us that span, and then 2 as the evaluates to 2. And the symbol elephant.
So
Whoa.
elephant has the side effect of a loud buzz.
Hey, Brian, sorry about that. I muted you. I'm not sure what happened. See, I'm glad you could make it. All right, so I put...
Yeah.
Okay, that's good. I don't think, if I'm holding it up, I think that's clear enough.
Chaz, does that make sense?
It does.
A little bit?
I can kind of make peace with this and say, like, okay, I know that somewhere there is going to be something that makes that large integer into this into that textual representation of the symbol. I can live with not understanding that entirely for a little longer.
Yeah.
Yeah.
I agree.
It's just the bytes of each character in UTF-8 in reverse order.
Gotcha. Okay. Yeah. Say no more. Awesome.
Looking at it in the hexadecimal encoding makes that pretty clear, because then you can look at individual characters in hexadecimal.
Okay. Okay. Awesome. Thank you.
All right. So, Matt, do you want to pick back up at 612? I think we've
Yeah. We'll go ahead with that.
got a number on span for now.
All right, so 612, limb and wing resolution. Understanding spans without any specific knowledge of twigs, for the most part, constrains who know enough to understand it in principle. One exception is the limb and wing twigs that reference the subject. An individual reference into the subject is a limb. A limb can be a name like foo, or a tree address like lus13, which is knock fast 13. Again, there are no symbol tables in Hoon. Name resolution is a tree search in the subject, depth first, head first, and cells. There is no separate resolution model for arms and legs. The first match we find, arm or leg, we return. The search is stopped by a buck face unless the limb matches the label. If we find a face foo and we're looking for a bar, we fail. Instead of looking inside the foo for a bar. Okay. But in a core where the search limb matches no arm, we descend into the payload. Sorry, was someone saying something? Okay. I was getting a little bit of feedback, I think.
Yeah, I think people were nodding along, basically.
Okay. A basic name reference returns the first match, but a limb can carry a skip counter. Okay, let me read that again. A basic name reference returns the first match, but a limb can carry a skip counter expressed by unary. Sorry, I must know what that one is. What is it, ket? It is.
Yeah, it's ket.
Okay. Okay, good. Expressed by unary ket prefix, e.g. ket foo to skip one foo, or triple ket foo to skip three, to find deeper matches that have been masked. A wing is a search path, a list of limbs syntactically separated by dot. Wings associate right, not left, as in classical languages. Foo.bar.baz in Java is baz.bar.foo. Hence, baz in bar in foo in hoon. Okay.
So I'm going to just jump in real quick.
Yep, go ahead.
Maybe embarrass myself because maybe this is obvious to everyone else, but it was not obvious to me, and it took me a while for it to click. The search that it's describing here, the search of the subject, is a compile time search. Names don't exist in your compiled code. So names in whom are resolved against the subject by the compiler and simply replaced with knock tree addresses.
Stands to reason.
The first time when I heard the search described, the first thing that occurred to me was that seems really inefficient. You know, like as you're running your code, it's just scanning the subject for names, and that's just a poor mental model from too much dynamic programming that I wanted to get out of the way quickly.
Another way of saying that is that the names only exist at the type level. So at runtime, there is no kind of names of any sort. Or at the value level, there's no names for anything.
That was not apparent to me, so that's clarifying.
Check in the chat. I think we're good.
Okay. 6.1.3 forward tracing. Type inference in Hoon uses only forward tracing, not unification, tracing backward, as in Hindley-Milner, Haskell ML. Hoon needs more user annotation than a unification language, but it's easier for the programmer to follow what the algorithm is doing, just because Hoon's algorithm isn't as smart. But the Hoon type system can solve most of the same problems as Haskell's. Understanding buck hold explains most of the type system. Computing an arm on a core always produces a buck hold. The compiler never calculates a type signature in any sense. Whenever type analysis encounters a buck hold, we expand it. This can be and is cached, of course. Effective analysis of interesting data structures is possible because non-perverse code repeats its span as we trace through it. Consider the simplest recursive span, a list. Lists in Hoon are not a built-in language feature, but user space code. They use genericity, which we haven't covered yet. But suppose the span of some list is expressed as a cell, sen, hold, pq, sir. Call this noun x. What span should we expect when we expand X? A list is either null, the span cell sen atom sen n 0 0 sir, or a cell ix, where I is the list item span and x is our original hold. Either means a buck fork with the set containing these two spans. So as we trace into the list, we see x recur. This is how a finite span can describe an indefinitely long list. Now suppose we're comparing two list spans x and y to see if they're compatible types. Can we compare these infinite expansions in finite time? Yes, as we trace into them, we just have to keep a working set of the comparisons we're trying to prove and prune the search tree instead of looping back into them. What if we're tracing through a twig that is irrational and doesn't repeat its span? Then the compiler goes into an infinite loop. This is actually a hard mistake to make, and the developer UX is similar to that of a runtime infinite loop. You press Control C and get a stack trace. This design has no trouble with tail recursion. Head recursion requires an explicit cast, which is still verified. Broadly, it's good practice to cast the product of any arm.
All right, who wants to go first on that one? That is a brutal.
Well, I'll just go ahead and ask, what is forward tracing? When we talk about forward tracing versus unification, what are we talking about?
Forward tracing is inferring the type of the product of an expression from the type of the inputs, argument, sample of an expression. So forward tracing says that I know if I have a function, I know the type of the arguments to the function. I can then analyze the expressions in the function and infer what type it'll produce. Now, I've actually never programmed in Haskell, but my understanding is unification or backward tracing says I know the return type of my function. I can infer backwards to the type of my arguments.
That sounds gnarly to me.
Well, I've only done a little bit of Haskell for funsies, but I thought that one had to specify the types of the arguments.
Yeah, and the return types too.
Yeah.
What's the point of the forward trace when everything is explicit?
I think the point of a unifying type system is that you express the constraints that are necessary to resolution of the required level of detail and genericity and specificity for the type of the variable, and that can be found after the naming and creation of the variable, or that can be found during that and then used for forward inference. I share the general notion that such code can be hard to understand. Putting your ultimate constraints at the end, well after you have defined the players that you're working with. I mean, it's cool that it generalizes that way, but I see the advantage in once the subject has become aware of the type of a twig somewhere, it will keep track of it and make sure it doesn't hand it to something which is not equipped to do anything useful with it.
The developer experience of all this is just in a unification type inference system, you have to specify the types less often. That's really the only difference. So in Hoon, you have to be a little bit more explicit about what your types are, is the upshot.
Yeah, and I think that does show a certain sympathy for the fact that code that gets into significant use is repeatedly learned. So it favors the reader over the writer on that one.
Yeah, I think that's right. We want to dive into lists a little bit. I forgot there was such a concrete example in that section. Did the list description make sense?
No, not for me, but I haven't.
Yeah, I think some concrete examples would help.
Well, sure. So the question that is being answered, and this part of the white paper does this a lot, where it answers questions that you just didn't know were being asked. The question that's being answered here is, how do you define a list type from a tree, specifically from a binary tree? And it's not a question that I had encountered before I started learning Hoon.
Yeah.
But the answer, just to jump to the conclusion, is that a list is either null, it's an empty list, or it's a cell where the head of the cell is an item of the list and the tail of the cell is another list. So it's a recursive type associating to the right. If you looked at it in a tree, you know, it would be every left branch of the tree, a binary tree. Every left branch would be incredibly shallow and every right branch would be very deep.
Sure.
And so that's how you get to that's again how you use a strict static type system to describe the type of something that is of unknown length, right? You need to use recursion because if otherwise, if you knew how long it was, then you'd be looking at a tuple type signature, if you will, saying that this type is, you know, 4 atoms or something like that. So when you have a recursive definition for list, and then it goes into a level of detail that I'm not sure that I'm comfortable summarizing or rewording, which is just a description of how type inference deals with a potentially infinite span. I mean, at a very high level, it's saying that in that list example, the span repeats because, again, the list is a fork. It's either null or it's a cell, where the head of the cell is an item in the list and the tail is another list. So that's where we recur. So you end up with these cells that are nesting to the right, and they're null terminated. But from this perspective of the type system, you only have really 3 types that you're dealing with. You have null, you have the type of an individual item of the list, and then you have the list type itself, which is a fork between null or this cell that's recursive. But since the span repeats, even though it's describing a potentially, you know, a data structure of unknown length, the compiler can still make inferences about it efficiently.
Okay. Do you mind going over the null span and then the cell span? I don't. Can you just read that? What are all the different elements in there?
Right. So the null span is a tuple of atom, the symbol atom, the symbol n, and then 2 zeros. Right. This is a very crafty or confusing way to write that span, because again, if we go back up, here I'll
back to listing 2.
If we go back to listing 2, we can see that the head. Here, I'm sorry, I'm losing. Let me share my screen again. Application window, the white paper, and zoom back in. So we're talking about this, right? This is a span. What we're looking at here is an actual span represented as a noun, not as the mold for the noun. So the head, the first element of the tuple is atom. It's the symbol atom. And the second is the symbol n. If we go back up to listing 2, we'll see this, right? Term is a symbol, and atom is the constant symbol. But we have this thing here at the end, Q, which is unit atom. And again, if the unit is null, which is usually the syntax sig, but is also just the atom 0,
Okay.
then it's a regular atom, and any specific atom, any specific unsigned integer can be within that span. But if that unit span is a cell of null and then some specific atom, then it's a constant, and only that specific atom is within the span. So what you're looking at here is actually that latter case. This is the constant atom with an aura of n and a value of 0. This first 0 represents null, and the second 0 represents 0. So that is like fantastically confusing.
Okay.
It's really a confusing way to write it. But that's all it means, is that that is one way of representing the span of null.
Okay, because I was intuitively thinking that the non-null atoms weren't going to be represented as constants. That makes sense.
And so then again, cell simply wraps two other spans. And so I here is just a placeholder for whatever the span of an item of your list is. And then X here is a placeholder for the original list span, which is to say the fork between the atom null or the cell. It might help to actually look at the mold for a list. I'm going to share my whole. Let me try this again. I'm going to share my entire screen, and I'm going to bring up Hoon.Hoon. And look at the list. Can you see that?
No.
What are we looking at? Oh, it's just slow, maybe. Whoa, it's like, on my end, it looks like Windows 95 crashing.
Yeah.
Let me zoom in. Can you see Sublime Text?
Yeah.
How do you zoom? Somebody help me out. I've never done this.
Apple Plus? I don't know.
Yeah, that's what I tried.
So the use of an ordered pair of zeros, what we call it a list, a proper list of zeros to represent the empty list, is, as far as I know, a common feature of all of the original implementations of Lisp. And the semantics of it, I think, are relatively clear, because the left 0 represents that there's nothing in this cell, and the right 0 represents that there is nothing beyond this cell. So it's the correct representation of the terminus of the list to use the empty list itself.
Okay, very nice. Yeah, very clear. All right.
Now it's working. I don't know why it wasn't working before. All right. So now is it kind of easy enough to see the expression I've highlighted here?
Yeah.
Really, the part that we care about is this part here in the middle, and just ignore everything that's around it, right? So we've already seen buck-pat. Buck-pat is a fork between an atom or a cell, right? The first sub-expression is the atom, the mold for the atom. The second is the mold for the cell, right? So if the span of a list is an atom, then, I'm sorry, if the list is an atom, then it has to be null, right? That's what buck sig means, null. Otherwise, it has to be a cell of this shape, right? And so I as the face here, is whatever whatever type your list is. And T is the tail, is another list of whatever type your list is.
Okay. Yeah, that makes sense.
So in my mind, that expression is much cleaner than looking at the representation of the span. But then again, this is white paper, and frankly, as far as white papers go, it's relatively readable, at least for me. It Well, I don't need a lot of math. So let's see, what else was in this? I gotta say, even though I've written a lot of Hoon, this last sentence does not, it's not clear to me what this is referring to. Paul, maybe can you take a stab at, I mean, to me, tail recursion means, regardless of sort of what branch of the AST you go down, it's the deepest, it's the leaf node of the tree, the deepest expression is a recursive call. So in that case, what is head recursion, and how would it require an explicit cast?
I have no idea.
Okay. I wondered if you did.
The difference is fundamentally that tail recursion occurs at the last possible point within the function that is being recurred upon. This allows the automatic application of the tail call elimination, TCE, or sometimes TCO,
Right.
which means you can convert the recursion into a loop and not use stack space in consuming your singly recursive entity. So head recursion means you still have state left in the function to fulfill. So you end up with multiple copies of that state every time you recur. It can be optimized in some cases, but not in the general case. So my guess would be that, you know, the tail recursion, because the stack is eliminated, and you know, at that point, there's something that's I'm pretty vague on, but I guess what I'm reading and saying is that it is possible to infer through using the Hoon algorithm at the tail position the span of the parameters that are being recurred upon and get the result out, so that all of that can be statically checked by the compiler to make sure that the result is of the correct span. But that for a head, you have to just say, and this is going to be of this, you know, meet this mold, and provide the span directly. But I feel like I kind of fell off a confidence cliff about 2/3 of the way through that in terms of my understanding of what happens there in the type system.
I think when you cast, you're going to simplify the span, and so that might, in some way, deal with the problem of head recursion. But that's as far as I can get.
Hold on. Say that again, Paul.
When you cast, you're going to, in some way, narrow the span. You're going to provide a span that's more specific than the one that the compiler would infer. And then it just has to do a nest check.
Okay, I'm still not clear on why the, you know, additional state that is repeated on the stack during a head recursion requires narrowing at that position, but not the tail position. I mean, I'm willing to
that
take
I don't
it
get
as,
either.
right. I'm willing to take it as a given for the purpose of this conversation, but I don't have a clear answer for why that is a necessary thing.
Have to ask Curtis, I guess.
Yeah, probably ask Curtis on that one.
All right, I'll highlight it for sure.
Mm-hmm. A general problem that is encountered with left recursion is infinitely looping, because if you recur at the beginning of a reduction, there is no guarantee that you will actually reduce what you're iterating or collecting. So you might not complete, even if you could. It's possible to set up the algorithm wrong so that it just spins instead of actually consuming something. So that may be related, in that's a parsing thing, and one comes away with the sense that Hoon's type system is very closely related to parsing, which is one of the reasons I like it.
Okay, well, I guess the big takeaway is the good practice of casting the product.
Right.
All right. Anything else? All right. Okay, so 6.1.4, pattern matching and branch specialization. The other piece needed to understand Hoon type inference is branch specialization. Hoon has a pattern match twig, buck fits PQ, emitting a formula that tests whether the value of Q is within the span of P. A branch with a test, which is a buck fits or arbitrary Boolean algebra using buck fits, where Q is a fragment of the subject, compiles each side of the branch with a subject specialized to what the branch test has learned. We use this to specialize unions, then manipulate each special case directly. If the compiler detects that one branch is never taken, it's an error. This is invaluable when, for example, refactoring a tagged union traverse. Okay, so that's a short little section there.
Kind of obscure.
Yeah, it's short, but it's dense. So let's see. Pattern match twig fits PQ, right? Q within the span of P.
So it would be a lot clearer if there was an example in it, right? So P in the fits twig, which the rune is what tis, by the way, question mark equals.
Okay.
P is a mold, and Q is a limb. It's a reference into the subject. Well, no, it's not. It can be a noun as well. The branch specialization only happens when it's a limb. So what you're doing is you're testing if some noun, either directly or by reference, matches some mold. And so fits on itself, like tis, it just produces a Lubian. It produces yes or no. But if you have that inside of a conditional twig, like if, which is, if then else, the span of Q is specialized in each branch, then and the else, based on whether or not it fit the mold. So a really good example is the list span that we were already looking at, right? So I is the face of the list item, and T is the face of the tail, the rest of the list. So for a given list that is not null, I is the first element of the list, and T is the rest, it's head and tail. But if you just take a list and try to dereference I against it, you'll get a compiler error. And the reason for that is the list could be null. I might not be there. So the compiler can't turn that face into a tree address if it could be null. That would be invalid knock, very obviously. So you have to test first. And so you put the test in a conditional, and the null branch, the list will have a span of null, not a fork between null and some cell. The span will just be null. And the not null branch, the span will no longer be the list span. It will be a cell of a list item and a list. So that's what branch specialization means. It means that you can test against a mold inside of a conditional, and the different branches and in the different branches, the span will reflect the result of that test. And that combined with, what was it called? It's coverage, right? It's branch coverage. It doesn't say that. But if the compiler detects that a branch is never taken, it's an error. Right, so it works both ways. There's a couple of different case twigs, switch statements, basically, switch expressions, I should say. And one of those will error if you miss a case. So take span itself, right? You would need a branch for noun, you would need a branch for void, and you would need a branch for atom and every other element of the tag union. And if you missed one of those branches, it wouldn't compile. It would simply be an error to say that you have not covered all of the possible spans within this fork of spans. So it works both ways. There's branch specialization inside of conditionals, and there's coverage of forks.
Okay. Maybe, do you know where this is implemented so we can check out the source code at a later time? It's just grep for fits or something. It's in there somewhere, right?
Let me put some examples in the dojo. I mean, yeah, it's implemented in the, some of it's in the macro expansion and some of it's in the actual type inference, which is in play, the play arm of the UT core.
I think that's, I think we should move on now. I think that's good unless anyone has questions. Okay, cool. We got plenty of time, right? Not tonight, but in the future. Okay, 6.2, type definition. In most languages, types and data structures are the same thing. In Hoon, they are different things. A type is a span, a data structure is a mold. There is no Hoon syntax for a span. We don't declare spans, we infer them. Why not? There is no span that can't be defined as the mint of some twig and subject, so type inference solves type declaration. We like to constrain the nouns we produce to match regular and rigorous data structures. We define these data structures with type inference, but we define them as the ranges of construction functions, and Hoon has macros specialized for expressing these constructors. A data constructor, or mold, is easily mistaken for a type declaration in a more conventional language. For instance, the definition of span above is a mold. A mold is omnivorous. The argument to a mold is always buck noun. Molds are also idempotent. If the argument was already in the mold's range, the product is the argument. Tis pow mold x par. Pow mold x par. Yep. In other words, a mold normalizes its argument. Since Hoon is a typed language and it is bad form to discard type, you rarely actually call a mold function. Molds are normally only called to validate untrusted raw nouns from the network. Anywhere else, remolding data shows sloppiness. We do often bunt a mold, create a default or example noun. Logically, we bunt by passing the mold its default argument, but normally this call can be folded at compile time and generates a constant. Okay. Straightforward enough.
Yeah, anybody want to go deeper on molds, or are we we're good and ready to move on to syntax?
Surprisingly straightforward. I agree. The bunt little tidbit about bunting is a little mysterious, but I think that's intended to be that way at this point in the paper.
Actually, about the bunting, if you think of the sample as just being the thing that's there when you define it, you're just pulling the arm without changing the sample, and that's the bunt.
So the default constructor in the OO.
Yeah, I suppose so, yeah.
Okay. All right. Yeah, I could ask about Lisp and stuff, and I'm sure Sam would have something interesting to say.
Well, I think that one of the best features of Hoon is the extensive use of the balanced binary possibilities in a pair structure to include structural cues that show directly the type of the containing information. So this is kind of how you keep track of the span of a mold with ordinary bookkeeping and tracing. But in terms of validating a noun as being of a type, one must do such a thing structurally, or by fiat. That's really the other option, is type tagging, and lots of it. Structural typing has great advantages, because if you know the type system and you know the structural basis of the type system, then when you're just looking at, you know, piles of numbers, the shape of the structure should tell you, oh, okay, this one has a null in the top position, it's a union type, you know, these sorts of things. I like that a lot. I was a little flabbergasted. Last anecdote. I was a little flabbergasted when I figured out that the mold is able and even sometimes expected to change the informational content of the noun that it passes through. I once described this to Curtis as a type system that is willing to take a bull and give you back a steer, which actually turns out to be a reasonably good idea. I was just kind of taken aback when I first figured that part out.
Wait, you should explain that a little bit more, for me at least.
Well, so, you know, I would have been inclined to make a stronger validator, one that simply either validates the input as being of the mold it is calculating, or does not. There is actually nothing stopping molds from dropping pieces of data, mutating the position of data within a noun, or even just adding new stuff. All of those things can be done. It's just mold. I mean, a mold is a series of instructions, and that stands for the noun that you when you say this is going to need to take things from this mold. It has to be able to succeed in becoming one of those. And if it comes off the network, then the way that that's done is by being parsed, you know, into the noun structure and then checked for validity. But you should really only have to do that once, because you know you can keep track of those sorts of things when they happen.
By sorts of things, you mean the actual transformations that potentially occur?
Yeah, I mean, a base case example of this is taking in an atom and emitting a noun. You know, that's what Q does. So in principle, the information that comes in on a card off the network is completely atomic. It's just, you know, a long string, and that is the first level of detail that is provided to that, so that it can kind of enter the Hoon system, is queuing. So there is a bijective mapping between a jammed atom and its queued noun. So that's a case where you wouldn't lose any information, and if the atom was badly formed, then you would reject it. But what comes out the other end is calculated on a certain basis. So I like that.
Yeah, so I think those are really good points, and I would just say that one of the tricky things to understand is that most of the molds you deal with are complex molds. They're molds kind of built out of other molds, wrapping them around, or like higher ordered molds or things like that. And when you actually call them as functions, when you mold a noun, parts of the mold can bunt and parts of them can pass through. And I think my guess is that's what Sam is referring to when he says that it can sort of modify the noun. You don't. What the guarantee that a mold makes is that it will always produce the same span. And so you can see then why that's a solution to that, which is to say that if you are given a noun that completely doesn't match a mold, then the mold will simply just produce its default. It will bunt. But if you have a complex mold that's built out of different subparts, and some of them match and some of them don't, those that match will pass through, and those that don't will bunt. And so you can end up with something that's a little bit strange. And that's where the idempotence example in the white paper is really important. And there's actually a room for that, and there's several different functions that do the same thing, which is to say that you call the mold once, you pin that in the subject, you call the mold on that product of calling the mold the first time, and you assert that they're equal. So that's how you turn a mold into a harder test. But sometimes, you simply want to use it to produce a default, or maybe you have softer constraints. So there's many different use cases for them. And the other thing to note about bunt is that when you cast with a mold, what you are in fact doing is you are first bunting the mold. You're getting the default product out of the mold. And then you are casting by example. So the primitive, built-in, lowest level type casting twig takes two nouns, Cast the second noun to the span of the first noun if the span's nest. And so, but most of the time that you cast using a mold. And so what you're in fact doing is producing the default product of the mold and then using that as an example to cast to the other.
Mm. Okay, interesting.
All right.
All right, 6.3 syntax. Oh, how about the chat? It's probably somebody's in there. Nope, nobody's in there. Okay. 6.3 syntax. Hoon syntax approach is the opposite of Lisp's. Hoon is full of syntax. The front end, parser, and macro expansion is almost as complex as the back end. To understand Hoon syntax, we need a brief overview of the AST, or twig structure. To simplify slightly, a twig has a head, which is a tag, stem, and a tail, bulb, which is a structure containing more twigs, most often a tuple of twigs. The set of these twig stems is fixed. They are all special forms in the Lisp sense. Most, all but 28, are implemented internally as macros, but Hoon has no user-level macros. Each stem has its own bulb syntax, but most follow a pattern called the regular form, which we'll explain first. 6.3.1 Regular form, sigils and runes. A twig in regular form starts with one or two syntactic choices. A keyword, which is just the stem with col prefixed, or a rune, an ASCII digraph. For example, the twig form buck if p fast twig q twig r twig is written col if, right, pqr in keyword form, and what col pqr in rune form. Experienced programmers find runes much more readable, partly because the first glyph of the rune defines a functional category, like what for conditionals. Because Hoon uses ASCII symbols so heavily, there is some resemblance to Perl or even the APL family, although, is that Apple? Is that a reference to Apple? I've never heard of this APL. Although Hoon is more regular than both, it presents a serious vocalization problem.
Not Apple. Would be the Ken Arvison's matrix language APL was designed as a set of symbols for doing matrix mathematics at a time when computers were still being wired up by hand. And then it was implemented, I believe, by IBM originally as a analytics and strategy language, and people who work in finance and just it's kind of like the Vim of spreadsheets. Cool. In a sense, you're pushing around the 2 and 3 dimensions and 4 dimensions or more of just kind of orthogonal data. That's the major paradigm of APL. APL for abstract syntax trees is a lovely summary of what Curtis has accomplished here.
Sorry, what's that last part? APL for something syntax tree?
For abstract syntax trees, for lists treated in a balanced way. Lists in the axiomatic Lisp sense.
Okay, cool. Okay, Because Hoon uses ASCII symbols so heavily, it presents a serious vocalization problem. To aid in speaking Hoon, both for actual communication to assist in sub-vocalized reading, we have our own one-syllable names, right? Okay. ACE is a space bar. Okay, so I won't read them all. 632, regular form, tall and flat modes. There are two common syntactic problems in functional languages: closing terminator piles, e.g. right parens in Lisp, and indentation creep. A complex function will have a deep AST. If every child noted that AST is indented past its parent, any interesting code tends to creep toward the right margin. To solve terminator piles, there are two forms of every Hoon twig: tall and flat, i.e. multi-line and single line. Tall twigs can contain flat twigs, but not vice versa, mimicking the look of statements and expressions in an imperative language. Flat form is enclosed by parentheses and separated by a single space. Tall form is separated by multiple spaces or a new line. Excuse me. And in most cases, not enclosed at all. Note that except to distinguish one space from many, Hoon does not use significant white space. The trick is that most twigs have fixed fan out. For example, we know that if kel buck, if p fast twig, q fast twig, r fast twig, care, if then else has 3 children. Since the parser has a custom rule for each twig form, rather than shared syntax as in Lisp, that rule can parse 3 children and then stop. Some twigs are n-ary. Tall form has no choice but to indent each child and use a terminator tis. Right margin creep is prevented by backstep indentation, where classical language might write Hoon writes, so backstep. Ideally, the most complex twig is the else. If not, there's an alternate form, what dot, which reverses Q and R. Backstepping is just the standard pattern, of course, and the programmer is free to lay out their code in the most readable fashion. The only actual rule is that single spaces are not sufficient to separate tall form twigs. 633, irregular forms. Fortunately or unfortunately, any twig can also have an irregular form. For example, add 2 and 2 is the irregular form of sen lus add 2 and 2, or cult col cult add 2 2. Irregular forms are always wide, and there's nothing to do but learn them. And an example.
Now, I don't want to keep us too long before we get to 6.5 because that really stumped me. But the regular forms thing, are the regular forms, do they just arise out of some consequence of this design, or what is it? When we say that are they regular forms because it can't be avoided because of the design, or is it?
Sorry, what was the question?
Well, I don't know. I'm kind of puzzled by the existence of irregular forms. Is there
irregular with an I?
Yeah, irregular. Yeah. Is there some reason that they must be there, or
just for convenience, niceness? I mean, almost everything that looks like conventional syntax in Hoon is an irregular form. So the regular forms are highly regular, right? You have either the rune or the keyword sigil, and then if you're in flat or wide mode, you have parentheses grouping some number of subtwigs, each separated by a single space. That's for every single twig. That's regular form, wide or flat. And then tall form, you have, instead of the parentheses and instead of the single spaces, more than one space, whether that's new lines or just multiple spaces. separating those subtwigs. That's the entirety of regular form. I guess that's not true. For the handful of twigs, some of them need an explicit terminator. Most of them have a fixed fan out, right? You know, if or what pole takes 3 subtwigs. It takes, you know, the if conditional, then it takes the then, and then it takes the else. But some things take any number of subtwigs, and those need an explicit terminator. But with that caveat, that's the entirety of the syntax. That's the whole language. So everything else that you see, whether it's the list style function calls, all of the null terminated or null prefix cell shortcuts, the entirety of the atom syntax, all of those things are irregular.
I see. So whereas I'm inclined upon first reading it to think irregular. So this is a sort of inversion of terminology that one expects from this paper, where you hear irregular forms and you think, oh well, I've studied language and I hate irregular verb conjugations, so they must be terrible, right? But in fact, irregular forms are language there's syntactic sugar in whom is basically what you're saying.
Yes.
Okay, so I see. This is a typical inversion of language from the creators.
Yes. The author enjoys that, I think.
Gotcha. Say no more. Thank you.
All right, I think it's just polymorphism, and then we are through. What do you say, Matt?
We can't hear you, bud.
Yeah, my pleasure. Copy. 6.5, Advanced Polymorphism. As we noted, the definition of span in listing 2 is simplified. The full version is in listing 4. If cores never changed, we wouldn't need polymorphism. Of course, nouns are immutable and never change, but we can use one as a template to construct a new noun. Suppose we take a core, a cell whose head is a battery, tree of ARM formulas, and whose tail is a payload, any kind of data, and replace its tail with a different noun. Then we invoke an arm from the battery. Is this legal? Does it make sense? Actually, every function call in Hoon does this, so we'd better make it work well. Okay, I'll finish reading this, at least this section, and then Joe, if you want to hop on and sort of spit over the listing 4, that'd be great. Okay, the full core stores both payload spans. The span that describes the payload currently in the core is P. The span that describes the payload the core was compiled with is Q.Q. In the Bertrand-Meyer tradition of type theory, there are 2 forms of polymorphism: variance and genericity. In Hoon, this choice is per arm, which is why our battery went from map term twig to map term foot when it went into the coil. A foot is buck dry or buck wet. A dry arm uses variance, a wet arm uses genericity. Okay, right. Do you want me to read the dry and wet sections first?
I'll take a stab at this. Let me think for a second.
I want to hear about the twig turning into a foot when it coils on the wire.
Yeah. There
So
you
this
go.
is actually still, I just want to note this. This is not actually span as it is defined either in Hoon 151 or in 146 or whatever it's going to be in CC release. This is still a simplified version of span. So faces, for one thing, are much more complicated than simple symbols. But the cores are now not in 151, but in CC release, can be much more complicated than what's here. So let me just bracket that for one thing.
Okay.
So in the simplified listing of span, what we had for the core was a payload span and then a map from the ARM name term to the twig, which is no. What did we have? Let me scroll up and see. It was map term knock. What did he put in there? Map term span, right? Yeah, it wouldn't be the actual formula. It would have just been the inferred type. Okay. So in place of the map term span, what we have here now, I'm going to zoom in again and
Wait. We have map term twig.
yeah.
Oh, you mean which line are you referring to?
I was referring back to the old.
Oh, not the paper.
Yeah, the simplified one in the paper.
Listing to which part? I don't see any map term span. I see map term twig.
We do.
Yeah,
Correct.
on the last one of the second to last sentence of 6.5.
No. So back in 611, the simplified span that we showed the first time around.
Oh, listing two. Okay.
So now, in the place of that map term span, which again, it was just to represent the battery, we have this entire coil structure.
See.
And so inside the coil, what we have is we have a tuple with three phases. P is a variance label, gold, iron, lead, or zinc. Q is another payload span. I'm sorry. And
So are you reading? Oh, okay.
I'm looking at listing 4. Can you see my screen?
Okay, yeah, sorry, I didn't realize.
No problem. So again, we're comparing here in the core, right? We have the P span in core is the payload, and Q, the coil, is this whole thing, not just the battery now, but it's the variance model. It's another payload span, and then it's this R thing, which is a pair of something. This font is terrible, but all this means is it's either null or a cell, and then map term foot. And foot is a twig that's tagged either dry or wet. So again, for the core here, we have a variance model, a second payload span, something that's either null or a cell, and a map term twig with a dry or wet tag, basically.
Woo-wee, all right.
So just to scroll back up here to what you just read, remember, it's saying, suppose we take a core, a cell whose head is a battery tree of ARM formulas, and whose tail is a payload, any kind of data, and replace its tail with a different noun, and then we invoke an arm of the battery, right? So it's this replacement that this structure is here to accommodate. So the full core stores both payload spans, right? The span that describes the payload currently in the core is P. This is, again, the payload that is in the core right now, whatever now is. And the payload the core was compiled with is this one here in the coil. And so then you want me to just keep, you want me to do this, or you want to pick back up?
I'll continue reading.
Okay.
Okay, so the dry arms variance. For a dry arm, we apply the Liskov substitution principle. We ask, can we use any P as if it was a Q dot Q? This is the same test we apply in cast or any type comparison nest. Often cores themselves need to be checked for nesting. The semantics of this test are the well-established rules of variance. Arguments are contravariant and write-only. Results are covariant and read-only. To be exact, cores can be invariant, buck gold, bivariant, buck lead, covariant, buck zinc, or contravariant, buck gold. Okay, did you want to speak on dry arms?
Sure. Dry arms is normal, is the simplest way to think of this. Any code that you write, unless you are doing something special, is going to be a dry arm. And I'm looking real quick for, okay, so if that is lead, now I
wonder how
I am not fluent in the Bertrand-Meyer position of type theory, let's say. So one thing that I meant to have that I don't actually have is a list of examples for all the different variants.
Yeah.
So by the way, gold is in here twice, which isn't right at all.
I had a really good blog post with the examples when I was learning Scala. And if I find it, I will post it somewhere, but I can't find it now.
Lead, iron. Yeah, so he's missing iron. I think that iron might be contravariant. So gold, I believe, is standard. I'll jump in if you know this. Bivariant lead is a read-only payload, so that you can't search into the payload. Zinc is, where did my source go? I don't know what zinc is. I can't say I've ever used zinc or iron, which is what I believe contravariant is. But basically, these are different modes of variance for the payload, for the payload of the core. And you could do things like simply hide the payload from outside consumers. And I guess the simplest way to think of this is, imagine that you're writing a library of functions. Now, normally, with a normal core, the payload of that library core is going to be whatever it was compiled against, which is to say it'll be the standard library. It'll be Hoon, it'll be Zeus, it maybe has a little Arbo in there depending on how you compiled it exactly. And you could retrieve any of those, you could dereference any of those names through that core, right? So you could pull the add gate out of that core. You could pull anything that's in the standard library out of that core with the normal gold variance. But if you switch that variance to lead, the only things that you can reference in that core are actually in the battery. So that's the only time I've ever used variance, the different variance modes. And I've written a fair amount of Hoon, so I think that's probably safe to say you don't need to worry about the details of this too much. But
so where iron comes up is if you're trying to write buckheb, right? You're trying to say, I want anything that takes an argument of this type and returns this type. The iron part of it is, you have a gate and you're forgetting everything that's not, the argument type.
I see.
If that makes sense.
Everything that's not forgetting the argument type.
So you've got the whole payload, which is all that stuff that he was saying before. It's got the kernel in there and all that stuff. And you don't want to match on that because you don't care what the payload of your argument gate is. You only care that its sample has a particular shape. Which is part of the payload, right? The sample is in the payload.
Okay, that's really handy. Yeah, and I didn't realize that. I'm guessing that gets maybe that one's actually the default then.
when you
seems like
do
what you-
a buckhep, what you're doing is casting a normal gold gate to an iron gate.
I see. Got it. Yeah, that makes perfect sense. And then on wet arms, I mean, we can read this, but I would just say really briefly that the mechanism is a little bit obscure, difficult to think through, and you don't need it. You need it as a consumer, but odds are you don't need it for anything that you're writing, unless you're writing, truly like a generic data structure engine. So with that, I'll throw it back to you for one last section, Matt.
Sure, yeah. I do remember actually getting into wet versus dry arms with somebody in the meta channel when I was trying to write something. I forget what it was. But anyways, for a wet arm, we ask, suppose this core was actually compiled using P instead of Q.Q. Would the NOC formulas we generated for Q.Q actually work for a P payload? If so, can we effectively customize the type signature of the core for the payload we're using? Consider a function like turn, Haskell flip map, which transforms each element of a list. To use turn, we install a list and a transformation function in a generic core. The span of the list we produce depends on the span of the list and the span of the transformation function. But the NOC formulas for transforming each element of the list will work on any function and any list, so long as the function's argument is the list item. When we call a wet arm, we're essentially using the twig as a macro. We are not generating new code for every call site. We are creating a new type analysis path, which works as if we expanded the callee with the caller's context. Again, will this work? A simple and not quite right way to ask this question is to compile all the twigs in the battery for both a payload of P and a payload of Q.Q and see if they generate exactly the same NOC. The actual algorithm is a little more interesting, but not much. A Haskeller might say that in a sense Q.Q and Q.R.Q, the original payload and the battery, define a sort of implicit type class. And indeed, Hoon uses wet arms for the same kinds of problems as Haskell type classes. Okay.
I gotta say, I'm super interested in the relationship between Haskell type classes and wet arms, and I've thought a lot about it and can't figure it out for the life of me. So if anyone has some insight, I'd appreciate it.
I would just say that I wish I knew Haskell. The thing that's not clear to me is actually what degree of type analysis at all is done for wet arms, and I don't know if we want to go down this rabbit hole. I wrote a bunch of test code at some point to try to figure it out, but it strikes me that little to no type analysis happens, and most of the type-related errors that you're getting are actually just merely saying that, hey, that face you're trying to dereference is not in your sample.
It seems to me that how it works is, I'm going to have to think about this for a second. The line about it being kind of like using the twig as a macro is illuminating. It's saying if you replace the span of the sample with the thing you're actually calling the wet gate with, does the thing still compile? And it just kind of replaces it and pretends that you had defined a function that did have that span and then checks that.
Right, and I guess it's not clear to me that it actually runs the compiler. I tried to trace through the code for it at one point and decided not to continue.
I'd be not surprised at all if it doesn't actually.
Right. Yeah, I think that's the case right now. There are some known issues with wet gates because it tries to do a little bit of magic to graft the faces from your sample mold onto the sample itself. Normally, that in a dry gate that would happen because the actual sample noun is cast to the sample mold, and so the cast applies the faces. But in a wet gate, that cast doesn't happen, so it tries to sort of graft them on, and it sometimes fails at doing that. So if you look through the standard library, you'll see that wet gates with complex samples use tree addressing. They don't actually use phases.
All right, so 653. All right.
Mm-hmm.
Constant folding. There's only one field of the coil we haven't explained yet, P.RQ. This is simply the compiled battery if available. Of course, we compile the twigs in a core against the core itself, and the formulas can't be available while we're compiling them. External users of the core want this battery constant, though. It lets us fold constants by executing arms at compile time.
And that is whom. Thanks, Matt. That's a hell of a section to read.
That was fun.
For anybody here or anybody watching, I just want to caution that I think this section is probably the hardest way to learn whom that you would come up with. It's not the way to learn whom. We're doing this exercise here, working through the white paper, but start out by working through the docs and writing sample code and work your way up. And I've been doing this for a while. Other people on here have been doing this for a while. And I don't know that everything in that section is completely clear. So don't worry about it.
As an addendum to that, it's not the easiest way to learn how to write Hoon programs. If you're trying to understand Hoon as an object of study, it's not so bad.
All right, cool.
So there was a question in the chat about the difference between a leg and an arm. Now, if I remember correctly, leg is just the generic term for any subtree of the subject. That could be referenced by a wing or a limb or by a tree address or something like that. But a leg is just to say a subset of the subject. An arm is a named computed attribute of a core. So I'm not quite sure why that specific distinction was brought out in the names, because they're certainly distinct, but they don't strike me as being parallel. Certainly in the sense that I guess limbs, references into the subject, could reference arms or legs, but it's not clear to me. Anyway, I would have used
the thing that resolves names will find both of those things and nothing else.
That's true. But it's hard to think of them as a category, except in the sense of the category of things that can be referenced by a reference. Let me see if there's anything else. I think we're good. All right. Anybody want to editorialize on whom before we move on to Arvo?
Oh, we're gonna go Arvo, huh?
Oh, were you tapping out, Matt?
I might. Well, no, I won't tap out. I won't miss it. That's for sure.
I don't know. Should we put it to a vote?
We have two. That was a solid 2 hours, though.
Yeah, it's heavy duty.
I have to tap out myself just to get something happening in meat space, but you guys go ahead. I can catch up on the YouTubes by all means.
Yeah, I mean we're not gonna finish the white paper, which is my hope, because Ames is just brutal.
Yeah, I'm actually content to tap out after whom. You guys can go along as you choose. I'll more than likely catch you at the next one of these.
Awesome. Thanks for
a good time. Stretch my brain every time.
Yeah.
So
Thanks for hopping on, Sam.
Yeah, thanks for
Cheers.
your.
All right.
Bye.
All right, later. And thanks, Chaz.
All right, thank you again for your time and all your help with this. I really appreciate it, and we'll see you next time.
Yeah, definitely.
Later, Brian, Paul, peace.
Thank you, Chaz.
All right, I'll put it to the rest of you then. What do you say? Let's see how long Arvo is.
Yes.
It's
Can't
not
see to
very
read
long.
that Argo, huh?
It's not very long. I'm inclined to do it.
All right. Go ahead, whoever wants to do it then.
Yeah, I'll go for it. All right. Section 7, Arvo, an event-driven kernel. Arvo is a single-threaded event interpreter. In many ways, it resembles other such event dispatchers, such as Node.js. In others, it's more unusual. We don't have space to explore Arvo deeply, but let's touch on a few of the design choices. Kernel interface. Arvo is the iteratively updated core we created at the end of the larval stage. If you remember, I think that was what we talked about in section 4. The core, listing 5, has 2 arms, named in honor of BASIC, peek and poke. The poke gate applies the next step. It produces a list of actions in a new Arvo core. The peek gate defines a global, referentially transparent namespace. If its product is sig, null, the path is mysterious. Its value cannot be determined synchronously. If it produces a cell of 2 nulls, the path is known to be unbound and can never become bound. Otherwise, the namespace produces a mark, external type label like a MIME type, and a general noun. Steps and actions share the ovum mold, which is a card, an untyped tagged union case, and a wire, a list of symbols representing a cause. Effects are routed to the same wire as their cause. For example, an HTTP request is sent to Arvo with a wire that uniquely identifies the request socket, keeping in mind that Arvo doesn't care if Unix reboots. Arvo must produce a response ovum on the same wire. It does not parse the wire, it just uses it as an opaque cause identifier. All right, do we want...
So we're starting to get into the unification of a lot of I want to say paths, but the unification of the file system and then the URLs, things like that.
Yeah, so really what you're talking about, if you remember, and I'm not going to scroll back to it because it'll take too long, but if you remember back in section 4, we talked about the semantics of the boot process producing a core at the end of it, right? Which is simply to say that you take the first item in a list of events and you invoke it as a function on the rest of the history of events. And you do that iteratively. That's the functional knock bias. And the product of that is the Arvo core. And that is the operating function. You know, I mean, at its most basic, urbit is an urbit is a knock interpreter bound to a specific cryptographic identity. And then it's the Arvo core as an interface. That's the whole thing. Everything that's on the inside of that, everything we talked about with Hoon, that could all be changed, and it would still be Urbit. And so what Arvo is it's this very thin event processing layer, and events are represented with these this structure that was described here, so that you have a card, which is basically some unknown data, but it's labeled with this type. And you have a wire, which is a symbolic encoding of where it came from. You know, and the example of a socket. But that could be sort of a more of a semantic tag of where an event came from. And I think that's all that we said. So yeah, section 17, kernel modules. Arvo is just an event distributor. Most Arvo functionality is in a system of kernel modules, or veins. The kernel proper is about 600 lines of code. Arvo loads veins as a source and holds each as a van noun cell, or vase. Dynamic type in urbit is using the statically typed compiler on runtime basis. Using vases, you can reload from source, obviously a necessity. A vein is a core in the same general pattern as Arvo itself, with arms that handle events, find names, etc. To update a vein, we compile the new source and ask the resulting core to copy the relevant state from the old core. This pattern is also used for updating user-level applications within the GAL vein. Veins have routing addresses, which are single letters. They are implemented by source files, starting with that letter. Vein A, aims, handles networking. B, vein, timers and initialization. C, clay, get style revision control. D, dill, consoles. E, IR, HTTP. F, forward, resource assembly. G, GAL, application control. So I'm going to keep moving here, and we'll go to the move system and stuff, I think. Each step that enters Arvo becomes a vein-level event, or move. Move can cause other moves. One external step becomes a cascade of moves. Process depth first as a transaction. And remember, step was the term that was used back in section 4 to describe either a packet or some type of a command sent from the host operating system into urbit. A single-threaded, non-preemptive event dispatcher, like Node or Arvo, is analogous to a multi-threaded preemptive scheduler. There's a duality in a mathematical sense between event flow and control flow. One disadvantage of many event systems is unstructured event flow, often amounting to event spaghetti. The control flow dual of an unstructured event system is goto. The Arvo move system is the dual of a call stack. Wires work as in the external step event, but a duct is a stack of wires. A pass move is a call. A give move is a return. To use an event-oriented service, the caller encodes the cause, reason, context, or purpose of the request in the passed wire. When the service completes, it returns the result on the calling duct. The caller is passed the return value in the saved wire, which provides context to the return handler. Since wires are symbolic, causes have to be encoded as symbols, which is not ideal for efficiency, but is ideal for debugging. A saved duct becomes the dual of a continuation, but it's much more printable than a continuation. It's also easily used as a table key, not a common use of continuations. It's straightforward to build a promise system on top of moves, but it's not conventional Arvo style. The ideal Arvo application core, whether vein or user-level app, contains a pure data structure without any functional state. For example, if the state machine contains promises, closures, which represent in some sense blocked sequential processes, upgrading it may be an unnecessarily interesting problem. So that's a really nice, clean theoretical discussion of moves that isn't exactly borne out by the current system, I would say. I find it quite difficult in practice to read some of the vein source or write application level functionality and figuring out exactly what the moves are supposed to be. To some degree, that's just a documentation problem. But I think that part of the white paper is clear and compelling. So I'm curious, do others find it so? Let's check the comments. Or anybody have any reactions to that? Couldn't have put it better myself.
Couldn't have put it better myself.
Wow. Mm-hmm. So let's see. I'm losing my windows here. Darpub asks in the chat, how is that different than a callback? And the way that it's different is that it's encoding the context of the callback as data. So you're never actually pushing like a partially evaluated function onto a stack or something like that, and then saving that stack as something that you could resume processing. You're actually writing out in a path, and now a path is a list of ASCII text atoms. So you're basically encoding the context in which your callback should occur as a string. And so on the one hand, that you could say that that's awkward, and you know, the white paper sort of tries to preempt. You know, like the question is, why is that worth doing, right? Why not use a callback or a promise or something like that and just push it onto the stack? And the answer is, you don't know how long it may take to get a response from your move. You don't know how long the thing might be sitting there, and you could be upgrading at any point in time. You know, this is a system that gets kernel level upgrades from source over the network. So everything needs to be upgradable. Everything needs to be able to be decomposed into deltas and reliably recombined. And so my understanding is that that's the strongest argument in favor of not, you know, simply using callbacks. There's also probably more practical implementation considerations, right? I mean, this, with this model, it's simply one additional piece of vein or app level state that you're saving, right? You stick the wire or the duct in a map or something like that, and then you persist your state and wait for the next event. But if you were going to stick a closure in there, well, now that closure is going to contain, by reference, your entire app and the entire kernel, and because cores wrap their context, right? The payload of a function, a gate, or any other typically defined core is the context in which it was defined. And in the case of an app, that's, you know, the kernel and the standard library and the operating system and the app itself. So there's sort of this nice, clean, you know, argument about upgradability against promises, but I think there's also an implementer's argument that this would be a tremendous amount of data, potentially with circular references in the interpreter level, and I would imagine it's a problem that everyone would just rather not solve. Paul,
well, there would be no circular references.
Well, I'm picturing that the closure references the app, but then that gets pushed back into the core. I mean, I guess as far as U3 noun is concerned, that's not really such a problem. Yeah, no, I'm not sure if the implementer's argument is really an important one.
I think it's more that the ducts don't make any sense if you put closures in them. If it's a bunch of symbols, they're readable, right? It serves as a label.
Right. Yeah, I guess I'm just trying to picture how a promise system or how a closure system would actually work, because I mean, simply speaking, I've never worked at the source level in Node. I'm not exactly familiar with how V8 handles callbacks. It must have a shared data structure that callbacks get pushed onto with some type of opaque identifier associated with them.
No, they're real closures in V8 as far as I know. They're function objects, right?
Right. Yeah, so I mean, certainly the debugging argument is a good one, and the upgradability argument is a good one. And then I went down a rabbit hole of implementation that doesn't make sense. So.
Well, I mean, if anybody here has ever tried to debug the callback hell that is trying to do anything of any complexity in JavaScript, it's obvious why that is not scalable, right?
Yeah, and I certainly agree with that, although I think sometimes just how bad it is overstated, and you can mitigate it, at least to a certain degree. On the other hand, the thing I really dislike about promises is how they just consume everything that they touch. You know, you introduce promises in one little corner of an app, and next thing, everything takes or receives promises, and everything chains, and you know, that sort of layer of abstraction, at least in a dynamic language, is a little bit tedious to deal with. Certainly, the fact that promises make guarantees about, you know, only resolving once, you know, and never then unresolving and re-resolving or something, that solves a lot of problems that callback hell can have for you. But I don't know. I mean, so from a user level, from a practical developer level, the consequence of this design is that you're producing a lot of data structures, right? When you want to call, you know, when you want to make a system call, basically, when you want to call functionality in another vein from one vein or from an app, you actually write out the, you know, you create the data structure that represents that call with a label, you know, for which vein you want it to go to, and a label for the method, and then the wire for encoding the cause. So that's certainly unusual. I've never seen another system that does it that way, and it takes some getting used to.
So one of the pieces of that can be like an index into a map that you have that maps that piece of the wire to some big complicated data structure.
Right. Yeah, absolutely. It certainly is a perfectly powerful mechanism. And one thing that I would like to see is a high quality visualization of move processing, even just for educational purposes, but an actual live one would be amazing. There's a generator you can run the vertical bar and then verb in Dojo, and that turns on verbose mode in Arvo, and it prints out every single move. Which there's so many moves going on normally that's you're just overwhelmed with logs almost immediately. But if there was a nice representation that actually showed the hierarchy of the move processing associated with that, maybe somebody should write a log parser or something for that format, because then that would really be a useful tool for seeing and understanding how individual operating system events are processed.
Absolutely.
All right. I think security masks is the end of this here. So yes, it is. Let's do this real quick. Section 7.4, security masks. As described above, Arvo is a single-homed OS. An instance has one identity, a ship, see the network architecture below, assigned at birth. All vein code must be fully trusted by this identity, a subject leg called our. But since sandbox user-level apps are a necessity and apps can generate moves, we need a security model assertion for moves. Thus, the mask noun in every ship, in every move, excuse me. A security mask is a cell of two gang nouns, each defining a set of ships, he or who, and Q or whom. The mask states who, other than us, caused this move, by whom was the move painted, and whom, other than us, is allowed to affect, who may it be leaked to. Each mask is a unit. If who is sig or null, it means that anyone could have tainted this move. It's completely untrusted, like an incoming packet. If whom is sig or null, it means that data from it can leak to anyone. It's public information. Whereas the empty set, so a cell of sig or null and sig or null, means totally trusted and totally private, respectively. Normally, a move produces effects with the same mask as its cause. Only well-defined authentication or sandboxing semantics should violate this default. So I think that for such a short section is surprisingly unclear. Basically, it just means that you have two nullable sets of chips for every move, you know, who it may have come from and who it may go to. That's it, I think. Plus the admonition to, by default, just use the same two sets as you know, add wires onto ducts and you know, layer moves on top of each other, unless you have a really good reason not to.
And a bunch of like grammar nerd porn.
Yeah, well, plus the historical, you know, whom angle, which had to be thrown in there, obviously. Okay, that's Arvo. The real meat of the rest of the white paper is aims, and our numbers are shrunken and we are tired, and at least I am. So I had hoped to be able to make it all the way through, but I just don't think there's any way. Let's see, we're on page 26 of 40 something, 42, 41. It's not going to happen. So while we're all still here, anybody have any other questions or observations or?
Whom has to be the hardest section to get through. So I think we're making okay time to get through in one more session.
Yeah, I think that's fair. It's a really hard section to read. There's no question about that. The problem here with 8 and 9 is just the volume of code, at least specifically in 9. I'm trying to think about exactly how. I just can't imagine it's worth that much to simply read it. So I know that you know, there's several different implementations of it floating around out there. You have it in Jacques. There's a Rust implementation. I've written it in JavaScript. There's the C implementation and the Hoon implementation. So I wonder if it might be worth it to try to actually just like analyze some of the different ways it's been written rather than read this incredibly dense description of some code, which, by the way, happens to be wrong. I need to open an issue around that, but I think the implementation of rub is wrong here.
It would be cool if you could just basically provide verbal commentary, you know, like line by line. Imagine you're writing some comments there. That'd be good.
I think it's actually not that interesting line by line. If you just get a little description of what those functions do, they're not that difficult to explain in terms of what their function is. So right. If we could go through that briefly, and that should be enough for like jam and q and rub and whatever the other one is. Yeah,
just a couple of examples, right? Just to show, here's the actual binary encoding of this noun, and then you can just say, you know, you have a cursor and a length, and you're, you know, extracting segments of this atom.
The coolest and trickiest part about it, and the reason why it's a little bit longer than it might otherwise be, is the aliasing, where it doesn't duplicate nouns. It just says, oh, it's that noun over there, so right. I'm not going to write it again here. And that's really important and tricky.
Yeah, it is. Well, and it's especially tricky, I think, functionally. That sort of thing is quite a bit easier to code imperatively than it is. There's kind of complicated recursion going on in.
Yeah, you have to thread the map through everywhere. It's a little annoying.
Well, and then you're aliasing the map, but then you're promoting it back up, and yeah, it's a little bit subtle. Looking over at the chat, Darpub is asking why the security mask is not being used. And the answer is really that there's a slot for it in the current Arvo, but it's not implemented. And I'm reasonably sure that this is coming in CC release. It certainly had been discussed several times in reference to CC release. So there's no question that it's on the roadmap, and it's something that Curtis is working on, but I don't know more than that. Let's see. Yeah, and then I would just say, as I've said before in some other venues, for a long time I've wanted to have some type of semi-regular virtual meetup about urbit stuff. There's so many different areas to dig into, and the white paper seemed like an easy point of consensus to get started. But it's a pretty dense document, and it's certainly not the easiest way to go. But I just want to throw it out there that I'm interested in doing this, semi-regularly. I think weekly is probably a little bit insane, but monthly or maybe bi-weekly or just as people are interested. There's a tremendous amount of things in Urbit itself, and then there's a lot of community projects. There's comparisons to other systems. I don't know, maybe people are crazy enough to want a live code or something. I think it'd be cool to keep this up even after we finish the white paper, which we'll have to wait for another week.
Mm-hmm. Oh, I'm definitely interested. I learned about Urbit just a few months ago, and I'm finishing my master's degree in CS now next semester. So if I can ramp myself up quickly enough, then I'd like to do some sort of Urbit related project for that. So I'm looking on drafting a proposal for that this summer, submitting that to my university. So I was talking a little bit about ideas for that. First started with something to do with Clay, some permissions there in Clay, but I emailed Curtis a little bit, and he was saying it's probably not significant enough for an MS project. So, but I haven't written hardly any Hoon at all except for playing in the dojo. So I'm working on writing an insertion sort.
Awesome.
Yeah.
That sounds like a really good plan.
Yeah.
And I would say there's some other exercises, particularly for different data types in the Hoon docs. That was where I actually started. I sort of beat around the bush for a long time.
Mm-hmm.
I wrote a knock interpreter, and I hung out and tried to clarify the docs and
yeah, I did that.
And as I hung out for quite a while before I finally bit the bullet and said, okay, I'm just going to learn this damn thing.
All right.
And the first thing that really clicked for me was working through the data structure exercises and doing things like writing list reductions or reversing a list without calling any functions, things like that. Just simply using the runes and pulling apart the cells and putting them back together and things like that was where it really started to click. So good luck, man, but I'd definitely like to look forward to seeing what you do.
That's the exercises part of the Hoon docs, right?
Yeah.
Yeah. All right, cool. Yeah, I'm definitely down to meet bi-weekly. Sounds good.
Yeah, I think that as a tentative plan, that makes sense. And I'm certainly in Urbit Meta a fair amount. I'm happy to talk there or anywhere else. Obviously we have to finish the white paper itself, so that'll be the first thing. We'll do a session on aims. And speaking of which, it's just not an area that I know real well, so I'll try to read it beforehand and see if I can come up with specific questions, either to put them on GitHub or put them on the fora or something, and try to be prepared for the next one of these. And yeah, I'll try to have some data and other code examples to go with that as well. So I think that's it from me. Thank you all for joining, and to those who had to leave early, and thanks to everybody who's watching on the live stream or chatting on Mardev. We'll do it again soon.
Thanks for doing all this work. This is really cool.
Yeah, well, thanks for joining and reading and answering or asking questions. It's awesome. All right, I'm going to stop the broadcast. I'll catch you all next time.
Good stuff. See you later.